Sup guys, welcome to today's show. So today we are going to continue our ping that we started with a couple of days ago. And before I continue, I just want to mention a little bit how it works on the packet level. Alright you guys, so internet protocols are divided in a 7-level scale. So at the bottom we have layer 1 and at the top we have layer 7. And what does this mean? So the lower level, the closer to the hardware it is, and the higher level, the closer to the application it is. And during this project we are primarily interested in two protocols at level 3 and level 4. So we have already talked a little bit about ICMP, and today we are gonna code IP. So what does this mean? The ICMP protocol looks something like this. So we have a type field and a code field. We do also have a checksum and we have a data field. So something like this. And if we are sending a ping packet, that means that the type field is going to be 8 echo. The user sends an echo packet and receives an echo reply, and that's how the ping process works. So the code field will be 0 in this case, and the data field, we can decide that for ourselves. Usually there is some kind of ID number here, so we can differentiate between the different packets. And then the checksum is a number which follows some mathematical formula that we're getting into, and this is just an example. Okay, so that's the ICMP. When the reply goes back, instead of an 8 here, we have a 0, and that is the echo reply or the echo response. Okay, but we cannot just send the ICMP packet. We also need to include stuff like the addressing information, and that's where IP comes into play. So an IP packet looks something like this. Okay, so, and I have not included every field here, only the things I think is most important. So first of all, we need to specify the version. You've probably heard about IP version 4, which is the current protocol, and IP version 6, which we are currently migrating to on the internet. But we are dealing with IPv4 in this case, so we put a 4 in this field. The TTL, it stands for time to live, and usually we put something like 250 or 255 or something high number from the beginning. And each time a router will forward this packet, it will decrease this TTL field. And the reason is, if you were to have a switched network, so these are network switches, and switches operate at layer 2, so it can be Ethernet, for instance, and you have a computer here and a computer here, and the network is built like a ring. If this left computer here will send a broadcast packet to this network switch, it will forward it to everyone like this, and keep doing that. So this will rotate and rotate and rotate, and it will take up every last CPU in the whole network, and the whole network will probably go down. So you cannot build an Ethernet network like that. However, on the internet we use routers instead of switches, and so the last network, that's a local area network using switches, but this is more like internet with routers. And when they designed the IP network protocol, they wanted to have some protection against these loops. So if this computer sends a similar packet to the router here, it will have 250 as a TTL. Then this router will move this to the next one, and it will decrease it to 249, and so on and so forth. So if there will be a network loop due to a misconfiguration, it will loop a little while, but when this gets down to 0, the TTL, then it will delete that packet. So it will stop the loop after 250 forwards. So that's what the TTL field is. The source is the source IP address, and the destination is the destination IP address. And these IP addresses are regular integers, which are in so-called network byte order, which basically means that if you have an IP address a.b.c.d, it will become d.c.b.a. And I will show that in code later on, but you need to know that kind of stuff. Then we have the checksum, which works the same way as in ICMP. It's the same formula even. And then we have the data field with the actual payload of this packet, which in our case will be this ICMP packet. So we are going to take this whole ICMP packet and put inside the data field of this IP packet, and then we will send this IP packet, and then we will receive a similar packet back. So this was a little bit of networking 101 but hopefully you know enough to be able to write the code. So let's start coding the IP part of this code. Alright, so before we continue the coding, I just want to fix one thing that one of my viewers pointed out, and that is when we send the data and when we receive it, it is in big endian format. And what does that mean? Well, the numbers, if we want to represent an 8-bit number, it can be something like AA. And this is no problem. But what if we have a number that is 2 bytes? We can represent that as AABB or as BBAA. And Intel-based computers use little endian, which means that the least significant bits are to the right. But big endian does the opposite. The least significant bit is here. So basically we just need to deal with all that are 16 bits, 32 bits, 64 bits, and so on, and turn them inside out. Most of our things in the raw ICMP packet is just 8 bits, but this checksum we need to take care of, and same with the well, when we get to IP, Internet Protocol, then we need to deal with a couple of more fields. So let's create a function. We can call it endian, and since we're only dealing with 16 bits, we'll start there. So we will have a 16-bit integer, and we'll have a function called endian, and it takes a 16-bit integer as input, and this will turn it inside out. By the way, let's call it endian 16 bits. That's easier. And let's put it a little bit on its own so we can create more later on. So how do we turn an integer inside out? It's pretty simple actually, using those bitwise operators. So let's say we have this endian function and we're having a value called x. We need to divide it up into smaller numbers, so an a and a b, which is 1 byte each, and by the way, let's make this int 8, and we need an int 16 y, which is the return value. So if we have a number such that AABB, let's first isolate the BBs, and we'll use the same technique as we did with the checksum earlier. So B is equal to, and we take the input value and we AND it with 0x00ff. So that isolates this byte. Alright, where were we? So we had B defined, and A will do basically the same, but in this case we're gonna AND this with 0xff00. So we isolate the top byte. And we also need to push this, let's see, 8 positions to the right. So we don't have a lot of zeros to the right. Okay, so now we have defined those things. Now we just need to assemble this stuff in our y variable. So y is going to be, and let's see, so we take this in the right order. So the b should be to the left. So we take the b variable and we push this 8 positions to the left. And then we AND this with the a variable. Yeah, that's right. And now we can safely return y. Okay. So now when we call the checksum function, or rather before we return, let's say we have a result thing, or a ret variable. So instead of returning this, we will set our ret equal to this. And then we return endian 16 of ret. Something like this. So let's see if it compiles and gives a different result. So we had D4 2D last time. So what did I call it? Endian. This should be endian 16. So D4 2D. Did I check the right thing? So this is the type, this is the code, and then the checksum D4 2D. D4 2D. And now it's 0800. Maybe I'm not reading it right. 01 D4. So the D4 is right. And it's at the right position. But why is there a 1 there instead of the 2D? That's weird. So let's see. We give this the same input as before, return endian 16 of ret. So B is X and 0x00ff. And A is X and ff00 and push to the right. And Y is B pushed 8 positions to the left, and we OR it with A. And the problem is the A, right? Or which was it? Tough to see here. Let's isolate it a little bit. So we have these two fields, then we have this, and then the rest. And now we have this. So this is the same. And the D4 is the same, but instead of 2D, we have 0, 1. Let's try this function on its own. So let's say we have an int 16 val, where val is equal to 0x AABB. Then we have val prime, which is equal to endian 16 of val. and then we print this thing, and we'll print it as a hexadecimal number, 4 digits, 16-bit hex. Val prime and return 0. So now we should get BBAA, right? BB1. Do I push it too far? So we start out with X, we end it with this, so we get the AA. Oh, there should be 2 of those, right? Weird that I didn't saw that. You probably saw it 2 years ago and laughed at me, right? All right, so sometimes it's easy to miss what's right in front of you. So let's run this again. And now we have 2D, D4. Okay, good. So now we are done with, let's close a few of these. Now we are done with ICMP, how we generate the packets anyway. So let's move on to IP, and that's the only other protocol we need to implement before we can, well, code the rest. So we will have similar functions for IP. And let's start by defining the data types. And as before, I want to have a struct SIP where I only store the things that I find interesting to save. And what is that? Well, we want to have the IP addresses at least, the source and the destination. And we can store them as a 32-bit integer. So let's say we have a source, let's say we have a destination, and let's check how the packet format looks. So Internet Protocol Wiki. Let's see if we find a nice picture of the packet. That's pretty weird that they don't show it at all on the first page, right? Maybe we should say IPv4. They should, here. They should put this on top of the page. I can promise you that 90% of the people searching for IPv4 is looking for this. But never mind. Alright, so the version is IPv4, that's not much to talk about. IHL, let's see, the IP address is variable in size. So this is just the size of the header. DSCP is the packet priority. ECN is Is it the do not fragment? No, explicit congestion notification. This field alone enter notification on network congestion without dropping packets. Well, this is not something that I have used a lot. Total length, well, identification. I guess this is the protocol number, perhaps, or is it an ID field of some kind? Identification field, uniquely identifying a group of fragmented packets. All right. I don't think we need that, but maybe it could be handy if we extend this later on and maybe use it in our firewall program or something. So let's use this. So 16 bits ID in 16 ID. What else we got? Flags. Fragment offset. Time to live. Protocol could be interesting. So this is the layer 4 protocol. So the protocol that's inside of the body of this. So it's an 8-bit field, and it will probably be 1 in our case. But I think I want to save this anyway, do I? No. Let's instead create an enum like we did up there. So let's say we have a type kind. And we can combine those ICMP code type fields with the protocols. I don't mind. Let's add ICMP, TCP, and UDP. And when we add it like this, the program will, or the compiler will assign numbers to these, so we don't care about that. But let's make it packed so that it doesn't take up a whole lot of memory. So let's say 0 is probably, maybe we can even define this explicitly. So we have 1, 2, 3, 4, 5, 6 different. So if we were to make this some binary, this is 1, 2, 4, 8. So those 3 bits will be enough for this field. So let's set that in both of these to optimize a little bit. So the kind is going to be 3 bits. And if we don't specify, it defaults to this, int 16 or int 8. But since we only need 3 bits, why not? Alright, let's see if we can find anything else interesting here. We have a checksum here as well, but I think I will just use the one in the raw packet. So we'll have 2 different kinds. And then we have source and destination, and potentially some options that we don't care about. So this is enough. And let's make this packed. Let's type def a struct s IP. and let's just call it IP. And we also need a struct s raw IP. And here we need to put everything. So let's see, 4 bits of version. So int 8 version 4 bits. And then we have this length, IHL 4 bits. So int 8 IHL 4 bits. Then we have the DSCP, and it goes up to 13. What is that? 7? 6 bits. So int 8 DSCP 6 bits. ECN, it's just 2. So int 8 ECN 2. And here we just made this as an optimization. Here it's strictly necessary to define the bytes and make it packed. Otherwise, it will not work. And then we have the total length. So that is probably the header and the data, right? Yes, 16 bits. Int 16 length. And then we have the ID field, which is also 16. Flags is 1, 2, 3 bits. Fragment offset, how much is that? 13 bits. So int 16 offset 13. And then the TTL 8 bits. Protocol 8 bits. And we are soon done. Checksum 16. And then the source and destination, and that's 4 bytes each. In 32 source, in 32 destination. Did I put the right order now? Yes. And then options. Do we need to keep those? Let's define them as int 8 options, and we define it like this. So if we need it, we can allocate for it. And this is packed, and we don't need to typedef this. Alright, so now we have the raw packet as well. Let's start as we did before by creating a constructor function, which will create an IP packet with make IP. And what do we need to specify? Source, destination, ID, and kind. So let's take it in that order, should we? Maybe we can actually move this up a little bit. Yeah. So this will be a type. And then we have the source and destination IP address. And in the constructor, I think I want to specify them as regular strings. Int 8 star, int 8 star, and what's the last one? ID. like so, and let's create this thing. So here we have the ICMP functions. We seem to have them a little bit mixed, so let's just put it up top. Alright, so we want to return an IP pointer. This is make IP, and we are going to take in, by the way, let's make those strings const as we did up there. So we'll have a type kind. We will have an int8 source, an int8 destination, and an int16 ID. And let's make sure that we have a kind. So if kind or source or destination, then we fail. And what do we do if the ID is not specified, or if it's 0? Should we randomize it perhaps? Yes, we could. And then maybe use some counter or something. Yeah, why not? And since I'm lazy, I will just use the library functions for this. So I'm gonna seed the random generator with srand and provide it with our PID as input. Then I'm going to return the first thing. So let's see. Let's call this rand. Rand is equal to our rand function. But let's modulus this with 65, 5, 3, 6. Since that is a maximum. And maybe we could actually make it a little smaller so we have enough room to increase it. Which means that we need to pass this value to our function as well. So, or a pointer to it really. So let's also give it an int16 star. So let's say this is int16 counter, or rather counter pointer. And then inside of here we will have one for the actual counter. Yeah, I think we do, or maybe we don't need this. We do, however, need some kind of ID. So So let's say this is ID prime, and we'll have an int16 ID. And if we have an ID which is positive, I mean an ID prime, the parameter, then we set ID equal to that. Otherwise, we set ID equal to the counter pointer, and then we increase it. Something like this. Okay. What else do we need to do? We need to allocate this thing. So let's say we have an IP packet, and packet is equal to, by the way, we need a size first. So the size is size of struct SIP, and packet is IP of malloc, the integer size. If we don't have a packet, we can actually assert that we have a packet, like we did before. And then we can zero out this thing, like so. And now we just need to fill in the blanks. So, let's create or let's not. Let's just fill in all these fields here that we can. So we need to switch on the kind. So let's say we have some kind of variable for that. And how big is the actual field? That doesn't matter, by the way. We don't need to do this here. We'll do this later when we deal with the other packet type. So let's just set the packet kind to the kind. Let's set the packet ID to ID. And then we have the source and destination, which are IP addresses. So we need to have some function which turns an IP address into, well, from a string to a integer. Maybe we can cheat a little bit and use the standard C function. I'm not really in the mood of parsing that kind of stuff right now. It would be an interesting exercise for another day, though. And let's say we have a destination. We do the same here. And if either of these are 0, or actually the source can be 0, then the operating system fills it in automatically. But the destination can most definitely not be 0. So if the destination is 0, Then we free the whole packet and return an error. Otherwise, I think we have all the fields, right? Kind, source, dest, ID, yes. So now we just can return this thing. Easy peasy. Do we need to deal with those const things in some way? Sometimes we need to cast an additional time because of that. Let's see. The only place we use them is here. And this takes a const too. So that shouldn't be a problem. Alright, I think this function is done. So let's create the show function when we're at it. We will probably need debugging. So we'll have a void show IP, which takes an IP star packet. If we don't have a packet, we just return. Otherwise, we try to print this thing. Yeah. So the kind, in this case, we can actually represent this as a number. So let's say we have a 0x%, 2 digits, or actually 1 digit should be enough, since this field is just 3 bits. So let's just make it 1. No, let's make it 2. It looks better. And this is HHX for 8 bits. So this is the packet ID. No, the packet kind. And then we have the ID. So this we can cast to a regular char, I guess. And this we cast to an integer. And then we have the source and destination, and we just have them in an IP format. But we are using birch utils. If I remember correctly, I do have some function for that. So let's see. Two dotted. This does exactly that. Print it in dotted decimal form. So why not use it? So here we will just have a string instead. Same here. This is with the packet source. This is the packet destination. But we need to call the two dotted. And since I have written this function on my own, I don't consider this cheating. And we need to cast this to a regular string. And let's print an extra new line at the end and return. And now we just add the signature for this. So void show IP, and this takes in an IP star. Maybe we could actually give this an int 8 star as well with the name of the identifier. That would be pretty cool. So we'll do this in both of these functions. So we'll just add int 8 ident, and let's move this out 2 steps. And we'll give it a kind of a headline. So this is the IP star, and then the name is equal to maybe something like this. And here we just put the identifier as a string. And then we do the same with the other show function, if we can find it here. So int 8 ident, and we have a little bit different syntax here, but let's move this out and this. This I think I will put outside. So if we do this and this, and then we do the payload, and then we add the headline here as well. So this is an ICMP star identifier is equal to this, and this is the identifier. And now to the cool part, let's create a macro which is just called show, and it takes one argument. So either an ICMP packet or an IP packet, and it will recognize the type that we give it and use the right function for that. So let's define it something like this. So define show, and it just takes an X, and we will call generic, which is a built-in macro. And I never really seem to remember the syntax, but I guess the first thing we must give it is the type. Or the identifier rather. And we need to do this. And then if this is an IP star, we want to call show IP, and we want to provide the name of X as a string and X. or like this. And if we have, maybe we can line this up a little bit better. If we have an ICMP star, we will call show ICMP, and same thing, we give it the X and the X. Something like this. I think this is how it's done. Let's try it out. We already have a little bit of code here. So instead of doing show ICMP, let's just see what happens if we just do show packet. Okay, some errors. ICMP redeclared. Maybe I called IP ICMP because I talked too much about. No, that's not it. Row IP. Which line is this? Uh, 53. Typedef struct S ICMP ICMP. Oh, it collides. This is the same namespace. So let's call this L4 ICMP for layer 4 in the OSI model. Doesn't look as nice, but never mind. $13. Yes, that is true. It's a lot of lines of errors, but I think we will fix this rather quickly. Warning, pointer targets in passing. Argument 1 of inet address different signedness. That is true as well. So 24. So what type does this take? Const. No, that's this. I guess it takes a regular string. Pasting blah and packet does not give a valid pre-processing token. Maybe it should be 1. I always mix those up. So let's just do 1 hash. Signedness again 191. Show packet. How can that differ in signedness and differ against what? Maybe this should be parenthesized. But that shouldn't really matter, should it? Show IP, show ICMP. Well, let's try. No. Expected specifier qualifier list. Okay, so that's not it. Differ in signness. And 8. Oh, it's the first argument. Now I get it. So we need to cast this like so. Passing argument 2 of show IP. From incompatible pointer type. Well, it should never be ICMP when it's IP, right? That's a weird thing. That's the idea with this whole function or construct. IP packets. Packet IP star. That argument is of type ICMP star. In function main. IP star. Should we omit the parentheses, perhaps? Do we need to cast it somehow? Okay, there we go. Variable R&D not used. Well, that's correct because we don't call this make function yet. So let's just tie this like this. and we should be all right. All right, let's see if this still works. ICMP packet is equal to this. Yes, pretty nice. So now we can just add more types if we want to. All right, so what's the logical next step? Well, we have 2 out of 3 functions. We just need the eval IP, where we turn our IP structure into a raw structure as a series of bytes. All right, so let's see. Int 8 eval IP, and this is going to take an IP star. And what does the eval function do specifically? Well, it just constructs this packet. Well, let's do something similar. So int 8 eval IP, we take an IP packet. We need some structures. S raw IP, raw packets. We also need a pointer, raw pointer. We need the checksum. We need a size. We basically need the same stuff. If we don't have a packet, and we don't need to check for the data in this case, since there are no, well, it might actually be some data. The let's see, the ICMP packet is the data. I think inside, I don't want to mess with this really, but inside of this, our own IP packet structure, we can actually give an ICMP pointer as the payload. So, yeah. And does that in turn contain everything? Yeah, kinda does. Alright, so let's update our show function first so we don't forget it. We can do this. No, but we can do something similar. Show IP. So if our packet has a valid payload. Weird. Payload. Then we can just call show recursively and provide this payload instead. That's pretty nice. Okay. Where were we? Yeah, so when we do this make IP, from the start, I think we should just set this yeah, we will just set this payload to 0 for now. And then when we have an ICMP packet, we can just point this manually. All right, so let's see. I guess we need to switch on the packet kind, because we need to set this, what did we call it? Protocol field. So let's say we have an int8 protocol. No, now we're in the wrong function. Int8 protocol. Set it to 0 first, then we switch on the packet kind. And if we have an L4 ICMP, we set the protocol to 1. And that's the only thing we should support at this point. So here we'll just return an error instead. Okay, so that's that part. And then we just fill in the rest. Let's start with the checksum, zeroing it out. So this is our raw packet. Dot checksum 0. DSCP 0. Destination. And this is already in the right big endian format. So we can just take it from the packet. ECN we don't need. Flags, don't think we need that either. Let's just double check that real quick. Flags, reserved, don't fragment, more fragment, no we don't. What else we got? ID, we just copy. And let's see, the ID field is 16 bits. So we need to run this through our endian 16. And this is the length of the header, right? Internet header length. Since we don't have any options, this will always be the same, which is 20 bytes if I remember correctly. Or is that the entire... the minimum value for this field is 5. Well, let's just do this. Size of struct as raw IP. Raw pack. By the way, how big is this field? It's just 4 bits, okay. Nothing to worry about then. And then we have the length field, that's the entire packet. Length. Here, 16 bits, entire packet in bytes, including header and data. So now we need to check if there is some ICMP packet inside of here. So let's see, let's create length little endian and the length big endian. So if the packet contains a payload, then we need to figure out the size of that payload. So the length in little endian is going to be the raw packet dot IHL plus the packet didn't we have some kind of size? Oh wait, this is the IP packet. We don't really have a size for that. Well, we can do this. So the packet payload, and this is the length that we are interested in. So size. And this is just the size of the ICMP packet's payload. So we also need to plus the size of a struct as raw ICMP. So that should be the entire length in little endian. And the length in big endian will simply be the endian 16 of the length in little endian. And this is if we have a payload. If we don't have a payload, the length will just be equal to the length of the headers. We need an else clause. Alright, nice. What else we got? Raw packet dot offset. We don't really need to bother with that when we deal with this kind of ICMP packets, at least. Raw packet dot options, we don't need either. Protocol, we have already, no we haven't, we have just defined a local variable for that. So here we set it. How big is this field? Int 8, that's good. And then we just have one more, right? Source. No, we have a few more. So the source, here we do the same as before. We just set it to the packet source. What else? The time to live. This is 8 bits, right? Yeah. And I think the standard is to set it to 250, but it doesn't matter all that much if it differs with a few jumps. Hops, I mean. So the TTL, and finally the version, and that is an 8 or 4-bit field, something like that. And this should just be a 4. This is the entire thing. So now we need to take the raw bits like we did here. So let's see, packet checksum, size. Yeah, we just need to allocate a string buffer which is big enough. And how big is that? Let's do length. Let's also set the length LE like this. And here we need to set the raw packet length to length LE. Let's initialize length LE to 0 from the beginning. So this contains the entire length. And let's see, let's do the same here. If the length LE and 2 is even, it's odd, I mean. Then we increase this by 1. So now we can do something like set p equal to malloc length LE. And we zero this thing out, length LE. We copy into P. The source being the raw packet. Length LE bytes. And by the way, let's set ret equal to P. Let's assert that we have a P. And let's increase P by length LE. Then we need to check if we have a payload again. So if we have a payload, we need to copy that thing as well. So let's do something like this. Int 8. And this is the ICMP pointer. And we set that equal to eval ICMP. And we give it the packet payload. And if we get a result, we will copy that thing into this. So copy into P, the source this time being the ICMP pointer, and we want to copy packet payload size. we have done this copy operation, we can free the ICMP pointer. And then we can return ret. Okay. Now I think we have everything. And then we can just start creating the real stuff. Where we initialize sockets and the like. Let's just see that this compiles first. Size of conversion from unsigned int to unsigned char 4 changes value from 20 to 4. Raw packet IHL is equal to struct substruct raw IP. Is that really 4 bits? So how can that hold everything? The first header field in an IP packet is the version field. Oh no, that's not it. The IPv4 header is variable in size. The IHL field contains the size of the IPv4 header. It had 4 bits that specify the number of 32-bit words in the header. Okay, that's quite different. So instead of size of this, we need to divide this by 4. And we use this in a couple of places, which means we need to times it with 4. Let's see, raw packet options is equal to 0, invalid use of flexible array member. Ah, that's right. That is right. 129. This is an array, it's not a pointer or anything else. So, we can just leave it out, since we don't allocate for it anyway. What else? Variable length BE set but not used. That's right, this should be length BE. Size is an unused variable. Okay. Check is a that I actually forgot. Before we return here, we need to create the right checksum. So check should be equal to check sum see. I think we actually want that size variable, because we're dealing with a couple of different sizes and we can't mix them however we'd like. So here, for instance, I think we're better off let's see, length LE. I think we need to have a size struct as raw IP. We can allocate based on this. And we do all this, but when we copy, we just want to copy size bytes from here, and we want to increase this by size. And what about here? We want to provide our packet. It's easy. And the size. This needs to be length LE. And then we can set raw pointer equal to struct s raw IP. And we can point this to ret. And then we set the raw pointer checksum to check and return. Now I think it's good. Raw pointer. We shouldn't dereference this. Passing argument 1 of checksum from incompatible pointer type. Expected int 8. Okay, so here I suppose we should give it the ret instead. Raw pointer ret, yes. Checksum ret, yeah. Alright, it compiled and it still works this far. So when we come back after the break, we're going to test this out, and then we can start coding the raw socket kind of stuff. So we'll be right back after this. Alright, you guys, welcome back. So the next thing we're going to do is we're going to test this IP packet constructor, so we know that everything works. So we already have an example ICMP packet right here. So all we'll do is create one for IP as well. Yeah. So here we create everything ICMP related. We will not show it though. And not do the print hex. So here somewhere I'm gonna do IP is equal to make IP, and we need to have a kind. So let's say this is a nice layer 4 ICMP. And we need to have a source address. So let's say 192.168.10.5, and the destination address, let's just pick something, 212.16.16.214. And we need to have an ID, or we can put a 0 here to auto-generate it. And we need to have a pointer to the counter, and that is our R&D. Okay, so now we should have an IP packet. If we don't, we can actually assert. It's easier when we test stuff. So let's assert we have an IP. And let's set the IP that's one thing we did not account for. When we set the payload, we should recalculate the sizes, right? And the checksum. So I think we need a function for this, actually. So let's say we have something like add payload. So well, let's make it a boolean, and it's add payload, and it's going to take an IP pointer, and it's going to take an ICMP pointer, and that should be enough, I guess. And then it should add the payload and recalculate what needs to be recalculated. So we have a boolean add payload, and it takes an IP packet, and it takes an ICMP packet, like so. Let's check that we have both of these. So IP packet or ICMP packets, return false. Okay, so we will take our IP packet and we will set actually, I don't think we need to recalculate anything, do we? Kind source dest. No, we don't, because the only time we need to do stuff like that is when we eval the IP packet, and that function we already have. So we don't need this actually. So let's remove this function. Let's clean this out. So the only thing we need to do is take the IP packet. No, we can't name this IP. Let's call it IP packet instead. And let's remove this raw packet right here. And let's change the name of packet to ICMP packets. So let's see where we have just packet. Here, ICMP packet. Let's assert that we have an ICMP packet. Then we make the IP packet, which is now called that. IP packet, IP packet. So we'll set its payload to our ICMP packet, just like that. And we don't need to do this. I don't think we do. Do we have a size field inside of the IP? We have kind, source, destination, ID, payload. Do we need to know the size of this thing? No, I don't think we do actually. So we can remove this size right here. And when we have prepared the packet, we will set our raw equal to eval IP, and we'll give it the IP packet. But how do we know how much to print? Well, we never really do need that except now when we're debugging. Well, we know the size of the IP header. Maybe we should put this size thing back. We don't really need it later when we're actually going to use this for real. But now when we debug, it is good to have it. So the size is going to be the size of struct s IP, no, raw IP. So the actual header plus the size of the raw ICMP packet, its header. And finally we add the IP packet payload size. I think that's right. So let's first print, let's first show the IP packet, and then we can print hex the raw, and we need to specify the number of bytes, which is size, and a delimiter. Maybe we should have a delimiter here. Let's just make it a space. And when we have printed this thing, we can free the packet. This is the ICMP packet data, and the ICMP packet, and the IP packets, like so. I think this is the right way to do stuff. Make clean and make. It compiled without any warnings or errors the first time. Alright, so we have an IP packet, and this is the kind and the ID, which is auto-generated, remember? And we have source, destination, and this is the payload to the ICMP packet, and this is the contents of the payload. And here, down at the bottom, we have the entire thing. And I can't know for sure if this is correct. We will know better when we try to use this thing, but it doesn't look wrong, at least. Okay, so now we can start doing the real socket stuff. But this will be all for today. If you like this episode, please like and subscribe, and we will continue this project in a later episode. Thanks for watching. Thanks for today.